Welcome to my kitchen. Today I'm going to talk about the fluid mechanics behind animals swimming and flying. This one is not swimming anymore. I will eat it later. All right, this schedule. First we'll talk about vortex jetting. Then I will introduce a new dimensionless number called Strouhal number, which is involved in vortex jetting, and discuss its relationship with animals swimming and flying. And finally, we'll do an example problem together. So what is vortex jetting? As we can see from the picture below, when a fluid flows past the cylinder, vortices are shed continuously at each end of this circular boundary. This effect is called vortex shedding. Here is an interesting phenomenon caused by vortex shedding, called Kalman vortex streak. As we can see, when wind flows past this island, vortices are shed along its wick. So when the clouds are at relevant altitude, Kalman vortex streak can be visible. But what does vortex shedding have to do with animals swimming and flying? Actually, animals also shed vortices along their wings when they are swimming in water or flying in the air. And vortex shedding plays a major role in determining how frequently they flap their wings when they are flying or beat their tails when they are swimming. To explain that, let's start with the frequency of vortex shedding. So pause and ponder now. What do you think are the factors that can determine the frequency of vortex shedding? All right, it turns out that there are 4 factors, which are fluid velocity, fluid density, fluid viscosity, and the diameter of cylinder, which is the obstacle in the fluid. So take a few minutes now to do a dimensional analysis on your own. We'll do it together afterwards. All right, hope you have given it a try. So first, we're going to list all the units here. Frequency has a unit of 1/second. Viscosity has a unit of meter per second. Velocity, sorry. And density has a unit of kilogram per cubic meter. Viscosity has a unit of Pascal second, which is converted to kilogram per meter second in order to cancel kilogram here. And diameter has a unit of meter. So the first thing we're going to do is to cancel second with velocity. As there is a 1/second in the unit of velocity, and the unit of frequency is also 1/second. So we're going to divide frequency by velocity, which result in a unit of 1/meter. Velocity is cancelled, and density and diameter remain unchanged because they don't have second in their units. And we divide viscosity by velocity, which result in a unit of kilogram per square meter. The second thing we're going to do is to cancel kilogram by density. So frequency over velocity and diameter remain unchanged. We divide viscosity over velocity by density, which result in a unit of meter. The final thing we're going to do is cancel meter with diameter. We multiply the frequency over velocity by diameter and divide viscosity over density times velocity by diameter. This results in 2 unitless factor. Does this one looks familiar? Yeah, it's actually 1/Reynolds number. And the unitless factor here is the new dimensionless number we're going to talk about today, which is called Strouhal number. So Strouhal number is a function of 1 over Reynolds number. Here is a generalized formula for Strouhal number, which is frequency of vortex shedding times the characteristic length, which in our case is the diameter of cylinder, over flow velocity of fluid. Unlike Reynolds number, Strouhal number can't be compared with certain parameter to gain we can't compare Strouhal number with certain parameters to understand the properties of fluid. For example, we can compare Reynolds number with to understand to determine whether the fluid is laminar or turbulent. We can only understand Strouhal number as a frequency of vortex shedding normalized by the characteristic length and the flow velocity. And here is a relationship between Strouhal number and Reynolds number. As we can see here, Strouhal number only varies between 0.18 to 0.22 over a large range of Reynolds number. So we can approximately treat it as a constant of 0.2 over this large range of Reynolds number. What does that mean? So for a given velocity, higher the characteristic length, lower the frequency. This is because if the obstacle is larger, larger vortices can be formed, which takes more time. And as a result, it's less frequent. And for a given characteristic length, higher the velocity, higher the frequency. That also makes sense because if the fluid is faster, more vortices will be generated within a given amount of time. But what does Strouhal number has to do with animal swimming and flying? It turns out that there's also a Strouhal number for animal swimming and flying, which equals to the frequency of stroke, which is tail beating and wing flapping, etc., times the amplitude of strokes over forward speed of animals. Researchers have found that the range of Strouhal number animal use is between 0.2 to 0.4, which is close to the Strouhal number of vortex shedding. Why is that? To explain that, let's start with the stroke frequency. So vortex shedding actually consume energy. The energy of vortices are consumed by fluid viscosity. And when animal flap at the same frequency as vortex shedding, they can regain some energy. Let's explain it with this swinging boy. So when I try to push this boy, every time he leaves me, he will swing higher and higher, right? Which means if I push it at the frequency same as he swings, he will gain energy. If I push him at twice the frequency he swings, half of the time I will push him when he comes at me, which means he will lose energy. This is similar to what happens when animals flap at the same frequency as vortex shedding. So animal can flap at whatever frequency they want, right? So when they flap at the same frequency as vortex shedding, they will recapture some energy. So that's generally they use this frequency when they are cruising. And second is about stroke amplitude. When a bird is flying, half of the time its wings, which is the two lines here, will be above its body trunk, which is the circle here. And half the time its wings will be under its body trunk. So we can treat this bird as an obstacle with characteristic length, same as its stroke amplitude. Right, so with this two equals to the frequency so with frequency of flapping equals to frequency of vortex shedding, and amplitude of stroke equals to the characteristic length, the Strouhal number of animal locomotion is similar with the Strouhal number of vortex shedding. And animal trying to fit to tune their locomotion in order to fit in that narrow range of Strouhal number. For example, mosquito with small stroke amplitude fly at very high frequency. The frequency is so high that you can even hear the sound of their flight, right? And for eco manta ray, which is shown in the video here, it has a large stroke amplitude, and it can slow at a low frequency. Actually, researchers have used this narrow range of Strouhal number to estimate the speed of extinct animals with data from their fossil records. All right, after we learned about Strouhal number, let's do an example problem. So this is me, and I'm swimming, and I'm trying to figure out at what frequency should I kick my leg in order to swim at an energy efficient way. To solve this problem, let's assume I only swim by only kicking my legs with an amplitude of 40 centimeters, and assume I swim at a velocity of 0.4 meters per second, which is about 1/5 of the world record of 100-meter freestyle. And pause and ponder here. What is the frequency of my leg kicking if we want to swim in an energy efficient way? All right, so we have to use Strouhal number to solve this problem. According to this formula, the frequency of my leg kicking equals to Strouhal number equals to my swimming velocity times amplitude of my leg kicking. But what is Strouhal number here? Remember that Strouhal number is a function of Reynolds number. So I try to calculate the Reynolds number. It equals to density of water times my swimming velocity times the characteristic length, which is the amplitude of my leg kicking, divided by the viscosity of water. So we sub in all the values, and we got 1.8 times 10 to the 5. And according to this figure, when Reynolds number equals to 1.8 times 10 to the 5, Strouhal number is approximately equal to 0.2. So we can sub in this value into equation. And we got the frequency of my leg kicking equals to 0.2 times 0.4 meter per second times 0.4 meter, which equals to 0.032 per second. That means if I want to be energy efficient, I can only kick 3.2 times per 100 seconds. That doesn't sound right. Right? What does that mean? So that means there's more important factor to consider when I'm swimming, other than regaining energy from vortex shedding. So if I don't want to sink, I just need to kick faster. That's all for my mini lecture today. Thanks for watching, and sorry for my late upload. I hope to see you guys in the comment section, and good luck with your fluid mechanics study. Cheers.